Good evening. Welcome to today's class. Today we'll be talking about how to use a current mirror as an active load in a common source amplifier. And we will also be looking at the current steering circuits. Welcome to ECE 420, CMOS analog and mixed signal IC design. So let's begin with the first topic. So that would be current mirror load. In common source amplifier. Right. So till now we were using a current source symbol while we were designing the circuits, and that symbol used to look something like this. So you put a current source and you have an output resistance R0 in parallel to it with the supply VDD. You have a Nmos device with the source present, the supply input present on the gate. This is Vin of t, which is the small signal value. Then there is this DC biasing value Vin, grounded, and at the source we have a ground. There's no source degeneration. Input is given at the gate, output is taken at the drain. So this is V out of t. Now this current source we will now replace with an actual looking circuit. So how will that circuit look? Here is your Nmos device, which is made circuit M1, where you will have your actual device, the AC circuit, the DC battery voltage. So this is V capital in, small v, V in of t, output V out of t. Now this current circuit, you will have the actual mirror circuit. Since you are using it on the source with a VDD, you will use a PMOS device. So here you have the PMOS device present, where the current I that is present here will be expected to flow in this device here. So we will call it as M2. The VGS of this device is given here. So now we know that this is a device. To mirror this circuit, you need to have an identical VGS and an identical device here. So what is going to be the identical device with the same VGS? So that is going to be your current mirror. So this is your gate drain connected current mirror. So now you have a diode structure here. Now what is the current that you want to flow here? This would be I ref, and your expectation is I ref equal to I, load current that is going to flow here. Now this I ref you can create either using a resistor or you can use an active device. So that active device can end up being a diode itself. So what kind of a diode will that be? You can use a Nmos device. This would be your Nmos device that you will work. So now this current mirror is made up of 3 devices. Now, how do you know that what is the current that you will get here? The current that is going to come is 2 diode drops present here. So this is one VT drop. This is another VT drop. So what is the total voltage drop from top to bottom? So the current that is going to flow Vref is equal to VDD minus VTP PMOS minus VTN divided by R0 ROP RON divided by ROP plus RON. So this is going to be the total current that is going to flow through this device. And this Vref is what will get mirrored here. So this is the important thing. Now, how do you get this? The conditions that are need to be maintained. You have to have the device in saturation. So all devices are in saturation. And when they are in saturation, the transistor works as a constant current source. Constant current source. And what is the value of that constant current source? That constant current source is given as Iref in this particular condition. Right? Here, the simple assumption is the VGS value for both these PMOS devices are going to be identical. And if you coincidentally see, this voltage is now being shared between three devices. One, the gate and drain of one device, the gate and drain of M3, and the gate of M2. So it is a common voltage V1. So this V1 voltage is going to appear across 5 connectivities. So this has an important layout criterion, because you should ensure that this same voltage is appearing at all the 5 terminals. Terminal 1 and 2, terminal 3 and 4, terminal 5. So 5 terminals of these 3 transistors should have be connected with a similar voltage. So that is one thing. So how do you again further take care of that? So what that means is the VGS2, VGS2, oh, so this is VGS2. VGS2, VGS3 and VGS4 should be identical value, right? So in that case, you will understand. So here also you will have a R0. This is R02. This is R03, R04. So these are the R0 values you will have to keep, and you will ensure that they are operating in this function. Questions? So what is the VT value of each of these transistor? The VT value of the PMOS and NMOS. So VTP, that is going to be VT of 2 and VT of 3 should be the same or will be the same, and VTN of VT1 and VT4. PMOS device and NMOS device will be the same, and depending upon that, what is the value that we will have to set, we will have to look into. Now, in this condition, do we have the small signal sources? What are the small signal source? There's only one small signal source here. Everything else is DC signal. So how does this small signal influence? Only for this particular transistor, you will have a small signal source. So that would be VGS1, VDS1, right? And as usual, ID1. All the others, you will have different small signal, large signal values. Another transistor which we will use the small signal values is going to be the current mirror transistor, VGS2, VDS2, and ID1 will be equal to ID2. Same ID will typically flow. For all the other 2 transistors here, your small signal value is 0. Small signal component is 0. Right? Everything else is large signal component only. So that is what you will have to understand, that only the current mirroring device is what is going. Now, if you look at this voltage where you are connected to, it is like it is connected to 2 diode voltages, right? This is one diode voltage, another diode voltage, and it is kind of independent of this operation. So you can use this to branch off multiple power supplies or multiple current mirror loads also. Now let us go into it a smaller detail. Here in this analysis, what is your critical device? Because these two is diode, this two is diode, this is only the mirroring circuit and this is the active portion. This circuit is the active circuit, which is considered as the active load. And this circuit plays the maximum role, taking into consideration the VGS value and its VDS value. That would clearly define how it is behaving as a current source, constant current source. What do we look into it? How is this important? We will see. What is this importance here? Gate to source is a DC value, right? The gate to source is a DC value. But since it is present, there must be a small signal drain current flowing here. You will have a small signal drain current flowing through this, despite this being only a DC value. What must this be? It should simplify with this value. So let us find out the relationship here. So what will be the ID2? ID2 will be GM2 VGS2, correct? So there has to be some small signal component present here. Along with that, what will you have as the rest of the ID2? The drain source flowing through the output device. So VDS2 divided by RO2. So this will be basically applying KCL at the output node. You get these two small signal voltages. Now, in this case, since VGS you are saying is going to be 0, then the factor GM2 VGS2 is 0. So what is the effective drain current? ID2 is going to be minus VDS2 by RO2. So in this case, you see it is only dependent on the output resistance. So that is how the intuition gets. There is no small signal model. Sorry, there is no small signal GM value here, transconductance. How does a small signal circuit look now in this particular condition? Small signal condition of this PMOS device will look as 3 transistor device. Source is connected to ground, gate and drain. So at the gate you have VGS2. Where is a positive sign at the gate, negative sign at the source. And at the drain you have GM-VGS. Current is flowing this way. GM-VGS2. R0, RO2, output is here. Now in this particular case, with the drain current flowing outwards, we know that GM-VGS is 0. So if this is 0, then this will be open circuited this way. So what is left over? Only RO2 is left over. So on further simplifying, what do you get? So there is no impact of VGS2 here. So effectively, this circuit looks like a resistor RO2 with the supply S2 here, source being here, drain being here, and current ID2 is given as, what is the voltage supply? VDS2. Clear? This is VDS2 and ID2. So what is ID2 value here? ID2 is given as minus VDS2 by RO2. So the entire model, small signal model of this transistor finally reduces to a output resistance of MOSFET M2, right? So now exactly what you wanted as a large output resistance present at this circuit, you are getting that benefit. So now your transistor load model, this circuit right now translates to a small signal model given as RO2. This is your M1 circuit connected with source connected to ground, and it's V in supply, V in of T. And this is your VDD, which is now connected to ground. So here is your value. So hope this is clear. So this is how this current mirror load and this transistor directs itself into a resistor having a current minus VDS2 by RO2. Hope you've understood. Now, what do you understand from the circuit? That means this circuit here containing the entire current mirror load in the gray area, this entire circuit in the blue slide is replaced with just this circuit here. So this is going to be your small signal equivalent. Now you may have to understand what is the value of R0. How do you find out the value of R0? The value of R0 is very simple. R0 is dependent on this is equal to 1 over lambda 2 divided by IREF. Right? So this lambda 2 is your PMOS device. So depending upon what is the value you will get. PMOS device typically lambda might be negative. So we'll only take a modulus of that and then get the output. So lambda RO2 will be 1 over lambda times IREF. Now let us find the small signal gain. Small signal gain of the entire circuit. So what does a small signal gain look like? The small signal gain will look like as follows. GMVGS of your input. Your input circuit, let me quickly draw. RO2, M1, V in, V out. This is grounded. This is also grounded. So the model will look like GMVGS. So this is your gate, drain, source. Source is grounded. Gate and drain. Gate has V in. Drain has V out. So this will have a GMVGS. So this is your VG portion. VGS1 plus minus GM1 VGS1. Then there is R0, R01. Then comes your only the V out connected to ground RO2. RO2. So this is, you can treat it as your drain resistance which is there. So what will be the small signal equivalent? Right? What is the gain? This is your GMVGS. This is your effective R out. So your gain can be written as, circuit voltage gain will be written as minus GM R out. GM1. In this case, it will be minus GM1. R out is given as RO1 in parallel with RO2. Now, what are these dependent on? This GM can be written as 2 times square root of K1 multiplied by what is the RID? ID through this resistor is IREF times R01 divided by R01 in parallel with R02. This is your voltage gain, effective voltage gain. You are using the current resistor, or you can write it as your GM1 resistor. So this value 2KI1 RF is associated with GM value. Now, what is, how do you look for it? Is there a way you can write? How do you identify your R01 with R02? I don't know. You don't know? So we can find out that if you can, in the previous class, we saw that the gain of this device with respect to the two resistors. In one case, it is PMOS, in another case, it is NMOS. The gain effectively comes in as this GM1 is from this device. In case if you do not have an equivalent circuit, you have a different circuit, you will get the gain to be a ratio of K1 over K2, which is going to be the process conditions, process plus geometry. The ratio of the process and geometry of these two devices. So process would be mu n Cox versus mu p Cox, one NMOS and PMOS device. Geometry will be W by L ratios of these. So if the current is same, then the entire gain is given as a ratio of the process and geometry of this device. Now, another one major advantage of this current mirror is what we mentioned, right? You can use just one of these current mirror sources to distribute the voltage across all the other current mirrors. For example, assuming you have one current mirror like this, important that the main current source will have the diode-like structure, right? You will have this diode-like structure, and this node, is your VGS supply, which is common. Now this node, if you can distribute and ensure that the VGS supply of all these devices can be maintained, right? Which is called R load 1, IL1. RL2, RL3. If you have these three circuits and so on, if you can ensure this condition is maintained, in that case, all of these IL1, IL2 and IL3 will have the same resistance or same current IREF. This is the beauty of this current mirror circuit, that you can just have a single source. This can be the single source from where you are getting it. And if you can distribute this node voltage uniformly to all the places, you can ensure that the same current what is flowing in the source can come here, right? Assume and ensure that the geometry of the devices are also the same. And this has got a critical feature where you ensure you need something called a matching. And this is a technique which comes in the layout design, where you want to ensure that the VGS is the same, the VDS is the same, and IRF, IL for each ensures the same. So you will find many techniques in the layout design when this comes up, and this is where you have an interesting challenge in the layout design as the technology scales down. As the technology scales down, the values scale down, the geometry scale down, and you will have a lot more parasitic components coming into play. It could be the resistors or it could be capacitor. So you will be thankful that the jobs in layout design majority are to ensure that this matching is maintained in most of the cases, right? Most of the cases, this is what it is. So this is one job relevant work. So if you go through any layout design course, the first thing they will ask is matching, and you can find a metric of this one saying matching inaccuracy. They are not required checking what is the accuracy, right? So matching inaccuracy is defined in percentage, 1% to 5%. This is typically the widest range. The spec that your team lead in the layout or your layout team lead will give you saying, I need an inaccuracy of 1%. What does that mean? IL1 by IREF delta, IL1 by delta IREF has to be less than 1%. What does that mean? IL1 should be approximately 0.99x times IREF. It has to be absolutely close. Yes, practically getting this to be exactly will be different, but there has to be, you have to try maximum techniques, you have to find out and do it. And this is the one advantage of having current mirrors, and many MOSFET current sources can be designed. Now, what are the practical applications of these places? Where would you use them? Where would you apply? So that is an important. See, application of current sources would be if you're designing an operational amplifier and the op amp has multiple stages. Stage 1, stage 2, stage 3. Now you need to have the current sources for all these 3 stages being from the same environment, such that the difference of the variation between these 3 is minimal. So in that cases, you will use a current mirror, where you will have this as a reference current mirror, and everyone will start becoming L1, L2, L3, etc. Some cases you will have only Nmos current source, meaning you will only have current sink. And in some cases you will have both Nmos and PMOS, where you will do a mirroring. That is, from Nmos you will mirror to PMOS, and then PMOS will give a current. So that will be a current source per se. Okay, we will just come to this in the next few slides. I will explain how that happens, because that is now going to work with both opportunities. So or let me cover that, right? I will go to another topic later. So the best way of doing that is you have a single reference source, IREF, coming into your Nmos device. There is a current mirroring happening here. So once you mirror the circuit, here is your constant VGS point. This is grounded, VDD. Now, it is very simple how to do it for NMOS. We have seen the previous slide. You clip a identical V bias point and you will be able to generate the same IL here, M2. This is R. This will be RL1. Now, if you want to do PMOS, what you could do is you can take the same tap off point, first create an NMOS. Because you have to mirror this, right? So what will happen? So now with this stage, you are expected to get IL3, right? Now this IL3, you would like to send it to a PMOS device. So instead of having a resistor, you will take a PMOS device with this current load M4, same VDD, and you will drive the current going here, right? So now what is the ratio that you are observing here? We said this is mu n Cox W over L for 3, mu n 3 W over L 3. When the same current is now expected to flow through the PMOS device, now you need to ensure that this ratio is the same ratio maintained here to exact get mirror capabilities. So you need to have mu P4 Cox W by L 4, right? Only when these two are mapped or matched, you will get the same current, because you need to get the right amount of load for the same VGS supply that is going to be present here to get reflected there. How do you do that? Depending upon the temperature and the process, we know that the mobility of the charge carriers in NMOS is larger than the mobility of the charge carrier in the PMOS. Now, since there are more charges in NMOS and PMOS, you need to compensate the total volume of charge. You need to make this same. So the way to make it same is change the geometry of the device. So what you will do is you will change the geometry of W3 to be different than L, and typically you will be increase the PMOS geometry. So the volume, PMOS volume you will increase, NMOS volume you will increase. Now what is the goal? The goal is mobility carriers are same in both sides. This has to be same here, this has to be same here. So you need to go. So now what will happen is you will increase, since the mobility in PMOS is lower, you will increase the geometry. The total combination of these two should be the same. So the way you do it, the ratio of these two should be the same. So it will be mu n times WL by 3 should be in essence equal to UP times WL by 4. Now mu n, you can add the Cox. Here also you can add the Cox. Now since they are equal, this mobility carrier is equal, you get a ratio on how to design this PMOS device to maintain the same current. And that ratio you will say mu n over mu p is equal to W by L 4 by W by L times 3. So now this is going to be the ratio that you have to maintain between NMOS and PMOS for same drain current, which will give you same current flowing through the device. I repeat, you need to appropriately size the NMOS and the PMOS device to ensure you get the value. Now, after you get this value, there is no current flowing through this NMOS. So you're having a mirror circuit here. Now, this mirror circuit will function same as, should essentially function same as this. That means it has to give a constant VGS supply. Now, where is this VGS supply given to? This VGS supply is brought back here. Okay. Now remember, the VGSN for NMOS will not be the same as VGSP. Remember, this VGSN will not be similar to VGSP because you are changing the resistance value. W by L is going wider. So this might be a different VGS value. But the VGS value between M4 device and the M5 PMOS device, which is going to act as a current mirror, these two have to be the same. Okay. The yellow circles function will be the same, but the VGS value will not be the same. So VGSN and VGSP will not be the same. But to get the same drain current of IREF here, you should ensure that the W by L changes and VGS also appropriately change. In this way, you will have mirror circuit, a separate NMOS mirror circuit with its own diode connected value. You will have a mirror circuit with its own diode connected value in the PMOS. So this will be a dedicated NMOS. This will be for PMOS. So in this way, your current mirroring will happen for both NMOS device and PMOS devices. So the same current of IREF starting from here now will flow in both NMOS device also and in PMOS device also. So effectively, the current will be the same. What is same? IL1 flowing through this NMOS device M2 and PMOS device here will be M5. IL5 will be the same. Now, to ensure that the values are going to be the same, you need to have the correct resistance connected to the ground. This will be RL5. Like how you have this constant current resistance here providing the load, you will have similar. This is only a load resistance, okay? It is only used to check on the VDS supply. Similarly, this is only going to be your load, which is going to check on the VDS value. So this is how you perform current mirroring for both PMOS device and NMOS device. Clear? Any questions on this one? So one more, let us look at another angle here. What is this angle? The current flowing to this is a factor of ID directly depend upon VGS minus VT the whole square. And same thing will depend here. This ID will also depend upon VGS minus VT the whole square. Now, intentionally you have to change VGS because the process is changing. There is one more factor. The VT also will change for NMOS. The VT also will change for PMOS. There is going to be fixed. In most practical conditions, the VT of these two will never be the same. So VT NMOS will not be equal to VT PMOS. So now you see VGS minus VT, VGS is different, VGSN is different, VGSP is different, VTN is different, VTP is different. But there is one particular relationship you can maintain. What is that? You can maintain VGS minus VT of N. The difference between the two can be maintained to be the same. the difference between the two can be maintained to be the same, and that is called the overdrive voltage, VOV. Now, if you maintain that the same, the current can essentially remain the same because the current is not dependent on the absolute value of VGS and VT. It is dependent on the difference between the two. So in that particular case, if you can maintain VOV constant, if you can make VOVN to be the same as VOVP, your current can be the same. So that is another trick or design space that you will have. So in the center, I'm writing down what is the design space a designer will have. I'll call it as the T. So you can have only two things that you can maintain. First thing is your W by L. You can change the W by L and maintain. Second, you can change the VGS minus VT whole and then maintain. And if you effectively see, no other design variable is within your constraint, right? ID is mu Cox W by L VGS minus VT, the whole square. So mu is not in your control, Cx is not in your control. Only thing you can control is W over L and VGS minus VT. So that effectively becomes your design space. Your current mirror, you can only control using W by L and the VGS minus VT. You can independently not control using VGS, independently not control using VT. And you know, VT also has no temperature dependence also, right? So in all these conditions, you will have to look, how can you maintain the difference, that is VGS minus VT, to be a constant. So you should ensure that this value is maintained. Now let us get a common value to understand how W by L, that is K, and VGS minus VT, which is a VREF, get into the picture. This is the one common space. The T that we show here is going to be the common method of designing, right? So now we have that. Next one, we will try. This is now assuming you want to get a same value. So what is the closed form expression we have received here? There are two expressions we can use. We will have an unique feature of current mirrors. What is the unique feature? Your unique feature is given here. So your ID is now dependent on K and VGS minus VT whole square. K is effectively W by L. So if you want to get, I will simply write it as ID is dependent on VGS minus VT the whole square and W by L. Now, if you want linear current multiplication, right? What you can do, and if you want quadratic current multiplication, what do you do? Right? Now I will substitute this value with the other value that you have used. Overdrive. The overdrive is given as VGS minus VT. So if you look at this equation here, you will see that current has a linear relationship with the geometry, and it has an quadratic relationship with voltage. So if you want to increase the current exactly by any fraction that you want, then you can multiply that fraction by just increasing the geometry size. For example, you have IREF and you want to get 2 IREF. Best way to do is make W by L 1 here. This one you can make W by L 2 times. You will get 2 IREF. You need 3 IREF to make it 3 times W by L. You need 4 IREF. You can get 4 W by L. So you will have a linear control over the current. Right? 1, 2, 3, 4, n, whatever fraction you want. So what does that mean? That means if I use the same logic, if I use the same current mirror here, right? Now this is my W by L and I will call this total W by L as K1. Okay. If I just multiply by mu and Cox everywhere, it becomes K. Now if I just want to increase the value, all I have to do is copy the same VGS, just increase the K value. Make it K2. So here I will get K2 by K1 times IREF. It can be any ratio, 2, 3, 4, 2.5, 1.25, doesn't matter. That depends K2 by K1 times here. If I need to make it 10 times, okay. If I need to make this 10 times value, 10 times IREF, all I have to do this ratio, that is the W I have to change is K3 times increase, where K3 is equal to 10 times K1, W by L size, meaning W by L is 10 times. You want to make it 20 times. Take the same mirror voltage, VGS value same, increase the W by L here. So you want 20 times IREF. IL equal to 20 times, so your K4 will be equal to 20 times K1. So this way you can get any current mirroring. Now this is called current steering. You can steer any amount of current tapping into the reference that you have from IREF present here. And what are the fantastic applications that you have? You have total control. First thing is, the control is only in W by L, which is called width over length ratio. Only the geometry will change. All the other environment will be the same. For example, if this is your layout representation of a transistor, right? Typically what you will do is, if you really want to do, this is how I will do it. Take this device, copy it in the layout, Control C, Control V. One here, Control V again, place next to each other. This is your 2 devices. Now you want 4 devices, Control C, Control V. 2, another Control V I will do, just 2. 4 devices. You want 8 devices, copy this, Control C, Control V. 4 plus 4. So this way, just imagine, you will typically be doing layout like this itself. You don't have to redo, redraw, nothing. So this is your K equal to 1, this is K equal to 2, K equal to 4, K equal to 8. In this, what you're doing is, you are not increasing individually the transistor sizes. You are just multiplying the transistor. Right? Multiplying, or you could say you're doing a copy plus paste. So the same environment, what you see, you will just come across here. Right? So you've got transistors here. So if you have IRF current flowing through this transistor, you will have 2 IRF flowing through the combined transistors here. Similarly, you will have 4 IRF flowing through the combined transistor here. You will have 8 IRF combined to the combined transistor here. How does this do this? What you're doing is you are doing 8 times 1 IRF. You are not doing 8 IRF directly. This way, you have something called design modularity taken care of. What is the advantage of design modularity? If you change this device once, that is this transistor, all the mirroring transistors, since you have reused the same, will automatically get edited in your circuit. So that way you have better design control also. Design control. So you understood? So this is a critical feature and mostly used feature, this current steering. Another place where this is exclusively used, you will see in when you have to create some applications. So one we spoke about op-amp, right? Current steering where you want. Second, you can do it in binary weighted signal processing. What does that mean? If you have a particular signal processing block, right? And you need to give weighting function for each one of them. The way you would implement it is, for example, you have a mathematical function which says y is equal to m1x plus 2m1x plus 4m1x plus 8m1x, etc. And your final output is going to be y. This is your input as x. So what is your weighting function? Your weighting function is given as function is m1, 2m1, 4m1, 8m1, etc. So you are only getting this input x, but you need to generate the outputs. So what you can do a weighting function, you can say I will create a current source. So this is going to be m1. And I'll have another current source saying 2m1. Another current source saying 3m1. Another current source like this. I'll have n times m1. All of these can be summed and brought out. So if I multiply each one of these and get an output, I will get. So this is a very common, this is commonly seen in signal conditioning, in circuits. Then there is signal processing, right? The signal processing can be weighted mixing when you have to give certain weights to do it, weighted mixing. And this circuit further will be used in all advanced analog designs, advanced analog circuits. Okay, like op-amp, binary signaling. Third, you will see ADCs. You will have ADCs because you need to sample. Fourth, you will see that in DACs. analog to digital and digital to analog converters where you need weighted signaling. Okay, when you have binary search when you do, right? So binary circuit design. So the application of current mirrors is vast. It is one of the most powerful analog circuits that you will ever use in IC design. And the earlier you have the control, the better will be your circuit design knowledge in practical. So this is one very, very critical circuit. Okay, now we spoke about current steering, right? Let us do one quick example just to see how much you are able to grasp. Example, we will try to include both PMOS and NMOS. So how do we do that? Let us first do the circuit diagram. Let us start with something very familiar. So here we have the diode circuit where I am going to get some reference circuit here grounded. Now I will have a PMOS current circuit here, sorry, NMOS with I want a current ID1. So I will call this M1, sorry, M2. This is M1. This is ID1. Then similar, I want another circuit here, M3 with current ID3. Grounded value of the ground is VSS is equal to 0. Now, what is the K factor? I'm going to say the size, the ratio of this W by L is 5:1. Here it is 10:1. Here it is 25:1. So this is going to be the W over L that we have mentioned here. Okay. Next, same thing. I will try. I want a similar circuit on the PMOS side also. So this is my VDD, and VDD let me define to be 5 volt. So this PMOS device, I need a current mirroring on the PMOS device also. What is this device? Somebody has a question? Arvind, looks like you're having a good time with your friends. So you're not paying attention to class. Okay, understood. You're having a good time with friends. Continue. I will finish my duty. So when you have M5 here, you will have your ratio that is being maintained. So I will now ground this to ensure I get the same current. What is the example I will add here? Saying this is, I will maintain the same, assuming there is a same W by L ratio. I will change the W by L ratio for this device. Note, the PMOS device are reference to the same PMOS device. Understood? Now, for a practical circuit, when you have two VT devices, you do not know how much current will flow. I want some current. For example, I want I will say rather than 5, I will go 25 micron current I want here. 25 microampere current. So what will be the current that will flow here? This I will be given as VDD minus VTP minus VTN over the R0 of this device. Now I will physically add a known resistance called RF to ensure that I get a value. So this will be the RF value that I will add to ensure that I get a 25 micron current. I might be having other resistor values here, but I will ensure that I will use this RF to get an IREF equal to 25 microampere first. So the W by L ratio is defined 5:1 in both cases. And here we have PMOS is grounded. Likewise, we will have the NMOS also to be grounded. Now, what are the other variables that I need to make this function? The questions will be, what are the other value? Other value will be mu n Cox. I need to know what is the mobility of this device. So mu n Cox, let us use a value simple for calculation, 20 micron by volt square. Then there is mu p Cox, also simple for calculation, 50 micron by volt square. Is this correct? No, this is inverse, because we said mobility of the PMOS is lesser than mobility of the NMOS. So if you see, this is flipped. So remember, whenever you see in your data point that the mobility is inverted, always clarify. Here, in this particular case, the ratio that you are getting is mu n is equal to 2.5 times mu p. Right? Now you have this. Next value that you need, what is VTP and what is VTN? So let's make life simple. VTP is equal to -1 volt. VTN is equal to +1 volt. Now the design statement is find the value of RF, right? Find the value of RF which will satisfy this criteria. This is your question. Note, you might find a exam question similar to this. So whether it is going to be how quickly or intuitively you are able to answer, we will see. But which exam, we will figure out later. Now, what information do we have? If you want to solve, okay, what is your observation that is present? First observation is the current through 4 and 5 is going to be the same. So ID4 is equal to ID5. How much is that equal to? Why is that equal to? The W by L ratio of both these devices are the same. It is 5:1. So whatever current is flowing through ID4 will flow through ID5. And how much is that? 25 microampere. Now, if you observe ID2 is 2 times ID1. And if you observe M3, ID3, what you will observe? The W by L ratio has changed. W by L ratio is 5 times W by L. So you will get 5 times ID1. How much is this value? This value will be 50 microampere. This value will be 125 microampere. Why is because W by L of 2 is twice W by L of 1. So this is the first observation. Now that we have found out, find out what is the R value. How do you find out R value? RF is equal to VDD. How much is VDD? 5 volt. VDD minus VTP. How much is minus of minus VTP? No idea. It is also called VGS, right? VGS of 4, VGS of 5. So you can also write this as VGS of P, what is VGS of P? Is negative, right? Then minus VGS of N or VTP whole divided by IREF, right? So what does this say? 5 minus 5 plus VGSP minus VGSN divided by IREF. Now this VGSP is equal to VTP. This is VTN. So it will be 5 plus 1 minus 1. So what will happen? VTP, VTN will cancel each other. So it will be 5 by IREF. How much is IREF? 25 microampere. So 5 goes 1 time, 5 goes 5 times. So what is this value? RF is equal to 0.2, 1 over 0.5 mega ohm. That will be equal to 200 kilo ohm. So if you have a value of 200 kilo ohm, then your circuit will have 25 microamp flow through M4 and M1, and subsequently you will be getting more currents here. So this is how you design a circuit. Now in this case, can this VREF be changed? Can you realize this VREF using 200 kilo ohm? Yes, your VREF now can be replaced using a transistor circuit. You can do it using two ways. One, let me go to next. Don't see. This resistor now can be implemented two ways. One way, diode. So you will have either an Nmos device, or you can have a PMOS device. So what is the resistance that this has to flow through? You should give a 200 kilo ohm resistance to be drawn. So how do you control the resistance here? Diode current, if you ensure that there is only 25 microampere flowing through each of these, right? Because the current flowing through has to be 25 microampere. So ensure that the diode current is 25 microamp during turn on period, you will get. Second way of implementing is using a current source, right? Now the current source can be, it can either be an NMOS current source or it can be a PMOS current source. What do? You apply the appropriate V bias N or the V bias P and ensure that the drop VDS is same and the current that is flowing through these two, right? The current you will again maintain 25 microampere. How do you maintain that current? Your VGS control. VGS you control here, VGS you control here. So VGS minus VT, technically the VGS minus VT you control here, you will ensure a 25 microampere current. Why VGS minus VT is not an issue here? Because this is always same. VDS is equal to VGS minus VT. In this case also you should ensure that it is in saturation. So just look at this. By having these three itself, there are 4 combinations in which this resistance can be implemented. So you maintain these two things. What do you maintain? You have to maintain VGS, you have to maintain VDS. So when you maintain these two values, you will get the appropriate load current in the resistor there. So you can implement this passive resistor using an active device. Similarly, we will give you a homework assignment. Let us see if you can do it before tomorrow's class. So the example is going to be as such. Intuitively, if you want a PMOS load or an active load using a single current source for both these, how do you implement? Let me draw the circuit here. Another example. Now you have a device, which is VDD, Nmos device with this supply V in 1 coming to V out here. And you have a current source I1. This I1 is equal to 0.2 milliampere. Then you have another current source, another device. In this case, this is M2 connected to again VDD, connected to its input VN2, and M2 device, you're taking the output here, VO2, and you are having a current load 0.5 milliampere. This is I2, right? Now, what would you devise? How do you devise this current? Starting from an 8 milliampere, 0.8 milliampere device. So the question will be, design the current mirror circuit for two configurations given below, starting from a 0.8 milliampere reference current. Okay, so your reference current is given as, and we will specify that from a reference current built from Nmos device. Okay, and Nmos device is built. What does that mean? This is very important to understand. What does this mean? So the answer begins here. First of all, observation. What is the observation you have? Or given information. Given information is you have an Nmos current reference source. Right? You have an Nmos current reference source. What does that mean? .8 milliampere. You have this current source that is given to you. Let it be, it is coming from the PMOS device. So this is a current source. So from here, you need to generate all of the above. How do you do that? First of all, understand you need to build a mirror circuit. So the moment you have this, mirror circuit is your diode circuit. Right? So now you have done a current to voltage conversion. Now you will distribute this voltage. And what is this device? This is the VGS that is being applied. How do you need to distribute? You need to understand what is the load current. So what is the input current with respect to the output current? First is you need from 0.8 milliampere, you need a 0.2 milliampere, and you need a 0.8 milliampere to 0.5 milliampere. So what does this mean? To make life simple, we will make this. This is 2 times K, having a unit reference. This is 8 times K. Same way you have 8 times K and you have 5 times K. Assuming K is a unit reference, now this is the ratio that you will have to maintain to get this one. So what does this mean? So for 0.8 K, you have what is this? 8 W by L, or 8 K is the ratio. So to generate this resistance value, you need an Nmos device whose value is, you need 2K. So it will be 2 times W by L. Okay, now you have current I1. Similarly, to generate 5, you will take the transistor size to be 5 W by L. Right? And now you will connect this voltage value to this place. This is your gate value constructed. Now you have the currents I1 and I2. So these current mirrors are now built. Now complete the rest of the circuit. The rest of the circuit is, this is a Nmos device, M1 VDD. Here you have V in 1. And current, complete this circuit. This is a PMOS device with a load given here, V in 2. Right? This is your output, V out 1. This is your output, V out 2. So this is how you build a current source that is going to connect this circuit and this circuit together in an integrated circuit solution. So you get essentially the finally here. Now, quick observations. Again, what are the observations we have? In this circuit, the input is applied to the bias, the gate, and the output is connected to the source. Right? And this is an NMOS circuit. So what does this mean? This is a source follower. Or what is the circuit called? It is a common drain circuit. Output is common to the drain, input is common to the drain. So this is a common drain circuit. Now if you look at this circuit here on the right side, 2, the input is applied to the gate. Output is applied to the source. So what is this? Output is applied to the taken from the drain. What does this mean? This is what is now common to both these places? Again, the source. So it is a common source circuit. But remember, one is an NMOS, the other is a PMOS. You should not say that they are commonly common to the drain or power supply. So how can one be common drain and common source? Note the transistor, one case it is an NMOS, one case here. So here you have a source follower, here you have a voltage amplifier. Right? Or in this case, there is a current buffer or same voltage. Whatever voltage you see in the input, you give it to the output here, or minus VT, follow it in the same tracking, or you have a inversion and a multiplication. So there is no inversion here, there is inversion here. So these are the way you will have to look into circuit design aspects and brought out. Okay. So this is now what happens if you connect V out 2, V out 1 and V in 1. You will see this impedance. This input impedance Rin looking into is infinity. This Rin looking into is infinity. What is the R out you are looking into? R out is small. Here R out is large. Now, if you connect these two, small input to infinite impedance, what will happen? You will have a impedance break. Okay. Now, if you put this in parallel, what will be the effective impedance of these two circuits put together? Low impedance in parallel with a large parallel impedance will effectively give a low impedance here. So, interstage impedance will be low. So, it will be infinity, low to high. You will have gain mismatch. Like that, now if you can give cascode, that if you have a different device, for example, you have a common gate device, which is now followed by a common stage device. So what is a common stage device? Sorry, common source. Common sources, here you give the input, P in, here you take the output, P out. This is your common source. Now what is your common gate? Common gate means you will give the source input at the source, you will take the output at the load. So I will call this VA. This is going to be your bias, VB, V out. And for this V out to take, you should have a load here. So in this case, this is common source, this common gate, right? Now what will be the common output impedance of this common source and common gate? First thing is this output impedance is going to be R0, R1. Now what is the output impedance of this device? What is it? Interesting, right? What you have missed out is the effective output impedance of this device will be a parallel combination of R out will be or equivalent as an input here, REQ as an input to the common gate stage, REQ will be R1 in parallel to what? GMB1 and parallel to GM1, 1 over. Yes or no? No. It is only going to be R1. Correct? R1 will be the resistance seen here. Now, what will be the resistance seen at the output here? That resistance will be REQ times GM, the resistance R out. What is the resistance R out looking here? The R out will be R1 times, now this is applying at the source. Remember, it is a source degeneration value here you will get. Right, R1 will be degenerated at the source for this circuit. So that will be 1 plus GM2 RO2 times multiplied by GMB RO2 times GM1 R1. Okay, so this is the approximate gate, meaning here the gain will be GM R out is your voltage gain, GM R1. Now that input is given here and this is a common gate stage. So gain is going to be the same. This is negative GM. So the gain here will be minus GM1 RO times, now this is going to be the effective GM. So that effective GM will be GM RO times this resistor value. How much is that? RO2. So GM RO1 times GM RO2 will be the effective load. Now RO2 will be in parallel with, what is this R out? RO2 in parallel with RD. So this is given as RO2. Let me RO2 in parallel with RD. So all these conditions will come into the picture, and this will be your intuitive R out and intuitive gain calculation. So this is now what is important here: common source followed by common gate. Common source followed by common gate, you will see what is the gain transmission. Common sources inversion will happen here. So your input is inverted at VA. So it is minus GM VN. So this minus GM VN is given to that source, and that literally gets translated to the output multiplied by the gain factor. So minus GM VN times R out is what you will get there. So one is inverting, another is non-inverting. So you will have a slightly larger gain that is present. Okay, I will stop here and let us quickly summarize what did we learn today. First thing, we have learned to apply current mirror as a load. Then we calculated a problem, right? A mathematical example to show how load is used as an active load. Then we saw how to calculate current mirror matching for each. Then we found out how you can do current steering or current multiplication, right? And this is achieved using ratios. Ratio of the device versus the source. So K1 will be W by L 1 times, W by L 2 times will give you the ratio as I load versus I ref. This is the current multiplication. And finally, we saw practical design for creating a current mirror for multiple current sources. Multiple current sources in the circuit, whether it is Nmos or it was PMOS. Okay. Great. Long class, but a very much deserving class that we need. So before we conclude, please come in for a photograph with the rest of the class.